So our today's lesson is on the queuing theory. It's a very interesting area because we'll feel that all of us, we have ever been involved into this analysis. It's only that we don't do it theoretically, it just come out automatically. And I was using an example where all of us students, you sometimes go to the cafeteria. I believe at one point you have ever gone to the students' cafeteria and then you find you have to queue. Our question is, how long do you remain in that queue? Then you get to be served. For example, you go buy your mandazi, you go buy whatever you buy, and then you get to sit down with your staff, or somebody brings to you whatever you have ordered, and then you sit down, you start taking your meals, and then you leave the cafeteria. So there are three things that I want to pick from that example. Number one, you have stepped into the cafeteria. The cafeteria is called a facility. I repeat, you as a student, you have stepped into the cafeteria. For the students, or let's use an example of another hotel, that cafeteria to us is called a facility. This one, we call it a facility. So what time do you get into the cafeteria? And then when you get into the cafeteria, you queue for you to be served. You find that the other students before you, so of course you have to be a respectful person. You don't go passing by everybody. You take a moment and you queue there. So when you queue, how long do you take in that queue? So there's the aspect of the queue. Okay? And then also, when it comes to you queuing, you have been served. Okay? And then you go and sit down and you start taking your meals and then you leave the cafeteria. Would also want to find out how long did you remain in that facility, in that cafeteria? How long did it take for you to be served? What was your waiting time for you to be served? And in any case, assuming like for every 1 minute you remain in the cafeteria, I as a lecturer, whenever you come to class rate, maybe I charge you some amount. I tell you, because you have come to class rate and you're in the cafeteria, I want you to pay maybe 2 shillings for every 1 minute you have remained in the cafeteria during the class time. So you are very careful on how much you're going to spend in that particular cafeteria, yeah, so that you don't lose a lot in terms of how much you're going to be charged. Now let's take an assumption of a business angle. For example, I am a business person who is operating a matatu. So I take my matatu to the garage. Maybe it has broken down at some point. How long do I take in the garage? That garage is another example of a facility. Then I go find that the mechanic cannot attend to me immediately because I have to wait for the customers who are there before for them to be served before my car is actually serviced. So you'll find that there's an amount of time that you're going to spend. But remember, this vehicle of yours is a matatu, to which every hour you spend in the garage, you're not getting a return. You get the point? So how much of the loss are you going to account for in any case you stay in the garage for a long period of maybe a whole day? You're 24 hours, you have worked for only 1 hour or 2 hours. The rest of the time, the vehicle was remaining in the garage. Maybe it has even remained there for like 2-3 days. So how much of the loss? So you'd want to minimize the time that you're going to spend in the garage as a driver or as a person waiting for your vehicle to be serviced. And all that is what we are going to, for example, visit as questions relating to how much do we spend in the garage, how much of the time, for example, do we remain in the queue, in relation to us being held in the facility. Again, another area that we would be concerned on is I am a mechanic now in the facility, in the garage. Anytime I find that there is no vehicle coming in for service, I am also having time that has been wasted. How much of the time on a given maybe day that I'm remaining idle, that in that particular facility, in the garage, we find that there is no vehicle. How much of the time are we spending not doing anything? Would also want to look at that. And of course, we may be concerned on the, let's say, the chances. We'll bring in the aspect of the probability theory again, the aspect of what is the chance, that at a particular time, I find I have got no customer as a mechanic, there's no vehicle that is coming in to be attended to, or given a number of customers that I may wish to have in the system, what is the chance that I can serve, for example, 2 customers at a particular time in that particular facility, in the system itself, or in the queue, how many customers can I have at a particular point? What is the chance? What is the probability of providing a that? So that is what we'll be speaking of as far as our questions are concerned in regards to the queuing theory. Also, we will be concerned on areas where, for example, we queue mostly, like I've talked about a cafeteria where students will go and they queue for them to be served. Even the staff members, we also queue, and other places in hotels, we also queue waiting to be served. And of course, we also want to find how much of the time do we remain in the queue or even in the whole system. And could there be a point at which the system is so busy, like the way you go to the cafeteria and you find those people have not rested at any point since morning, they have all been attending to customers. Would also want to find what is the utilization factor of a particular system. Other places where we normally queue, like in the supermarkets, I believe that all of us, we have ever gone to a supermarket, and the busiest time of the month could be the end month at the beginning of the month, where people would go and they buy maybe items in bulky forms, like over the Christmas time again, Easter holidays. So as such, you find people are queuing, of course, with a lot of items. So at times you even give up and you leave your basket and you go away. So we'd also want to see such behavior happening in the various places where we normally queue. I want to believe that you also pay your school fees at some point, not always that your parent pays for you. So if you are sent to the bank and you are to pay, get a receipt, and then you come to school, you queued like 2 times, where in the bank you have to wait until you get to be attended by the cashier. And also in regards to coming now for you to be billed at KCA or any other place that you have ever paid school fees, you also queue. So there are 2 facilities in such a scenario, but our problems at our level will only be dealing with 1 facility at a time. Another place where maybe we can consider queuing to be applicable is like in the petrol stations, where vehicles would go, they require fuel. And so at times you find there's a driver in front of you whom you have to wait until he or she is being served. And at times you find there are like 2 people or 3 people before you. And at times you may go into the to the petrol station and you find there is no one. You go get your petrol, get your diesel. In 1 minute's time, you have been served. So at such a scenario, you have found the system idle. What is the chance of a facility like a petrol station to be remaining idle at some point? At times you want maybe to go back home, like over the Christmas time. So you tend to book, the vehicle to take you home Maybe others are using the railway as a means of transport, maybe to Mombasa. Currently, it's available apart from now that there is a lockdown. So as such, you find that it's possible for you to, of course, analyze how queuing is coming in. I believe from those few examples that you have mentioned, we can be able to relate to the queuing theory. At times, like let me not deal with this so much, but during elections time, you queue for a whole day so that you can vote in. So how long do you stay in the queue? How long do you take when you get into the voting point? You vote and then you leave. How much of the time do you spend in the polling station at any point can also be a good area to consider where queuing theory can be applicable. So if you're given a question, class, and you're told to quote areas of application of the queuing theory, I think this is a question which all of us can be able to answer comfortably. And of course, you can be able to give as many examples as possible in relation to where queuing theory can be applicable. In the queuing theory, the following is our general structure. As I had mentioned, number one, the customer arrives. You have the customer coming in. So there is what we call the arrival behavior, and this will be randomly distributed using a distribution we call the Poisson distribution. Luckily, we had done a number of distributions in the probability theory. Then we have the waiting in the queue. That is the belief that you not come in immediately you get the service. At some point, you'll have to stand in the queue and you'll be served. That is another assumption that we'll be having in our mind. Then there is what we call the entering of the service station. Like now you queue and then you get to the cafeteria point where you're going to pick your meals. You come in, you queue, and then you have reached to the cashier. You have been you have been issued with the receipt, and then again you give it to the person who will give you the meal. So that is what we call the service point. And then after you have been serviced, you go sit down, maybe you take your meals. If it's your vehicle, it has already been fueled, you just leave the system. We don't want to make an assumption that there are people who stays there for a whole day. Yeah? We want to believe that you are coming in with a purpose, getting the service, and then immediately you just leave the system. Important points for us to have in mind. Number one is what we call the service system, like what I was calling a cafeteria. That facility itself is called a system constituting of the points where people come in, they be served, they queue, yeah, as such, the whole of that is what we call the service system. Inside the service system, we have got two things. One is what we call the service facility, and the service facility is where the customer will now pick that particular, let's say, food, the point at which you now get to be serviced, where your vehicle, you see the pump being put onto your vehicle, and now the oil or the fuel now start getting into their vehicle. That particular point is what we can call our service facility, and you now get to be serviced, and then later on you leave that particular point. Now, when we are looking at the service facility, it can be of different kinds. Let me give a good example. Like in your case as a student, the cafeteria we are using as our facility, I want to believe that you get the service at only one point, where all of us, you get into one door, you come queue, you be attended to by the cashier, issued with the receipt, and then you go pick whatever you want to, for example, order. So that kind of a facility is called a single phase channel. I repeat, the facility we are referring to in relation to, we all queue in at one point, we all get our service at one point, we call it the single phase channel, and this is the assumption will be going on at our level. I repeat, our questions will be emanating from the fact that we only have one line to which we all join in as a queue, and we'll all be serviced at just one point. Then in the supermarket, people come in, pick their baskets, of course, they pick their items, and then when they come in, they'll queue at different points. Depending on how many cashiers are available to attend to you, those teller points by the cashier people at the supermarket may be as many as possible, of course, depending on the size by the supermarket. In such a scenario where we are queuing in different lines, yeah, our waiting lines are kind of different, we call it the multi-phase, multi-channel. I repeat, a case where there are so many queues to which the customers may join in for them to be serviced, we call it a multi-phase, multi-channel. And this is not what we are going to be using. Ours will be the case of a single phase channel, or through as an assumption of just having one point to which all of us will get in and will all be serviced at just one point. And then we have what we call the service pattern. This is the way our cashiers now are attending to us. For example, when you go to the bank to pay for your school fees, when you get into the cashier point, how much of the time do you spend? Maybe you spend like 2 minutes. So we can say in 1 hour's time, the cashier is able to, for example, attend to 30 customers. If, for example, all of us, on average, we assume per customer, we are spending, let's say, 2 minutes to attend to a customer paying fees in the banking hall, we may make an assumption that 2 minutes per customer. Then transforming this, we can say in an hour's time, yeah, the cashier is able to attend to like 30 customers. So that 30 customers per hour, 30 customer per a given amount of time is what we call the service pattern. And in our analysis, we are going to assume that this is exponentially distributed, of course, using what we call the exponential distribution. So there are two things that I want you to pick from this so far. One is that the arrival behavior, like in an hour's time at the cafeteria, 4 students do come into the every 1 hour. We find that on average, we are having like 4 customers coming into our cafeteria. So our arrival time is going to be, or the arrival pattern is going to be Poisson distributed. This will be Poisson distributed. And because we are assuming that on average, Poisson, from the Poisson distribution, Poisson distributed. And because we are assuming that on average, this will be the arrival behavior by our customer, because we are taking it to be an assumption measured upon the mean, we are going to take the mean of the distribution, the Poisson, as mu, because people are coming from a given population. Remember, we had the parameter mu denoting the mean for the population. I talked about this, where because the population is the one that is giving us the people who are coming into our facility, we will take that the mean of the Poisson distribution is going to be called the mu. And then the service pattern, we have said this one will be exponentially distributed, and we are going to take that the mean for the exponential distribution. In this case, I think I've made a small problem here, sorry. The Poisson distribution, we talked about the mean of the distribution, and we say that this one is going to be our lambda. Sorry for that. You remember we had the Poisson distribution. The exponential distribution is the one for the service time. So for the Poisson distribution, which we said it's going to be in reference to what we call a discrete data. We say that this one is given by the structure, if you remember, the exponent to the power of minus lambda, lambda to the power of x, and then divide by x factorial. And we also went ahead, sorry for this, we also went ahead and talked about the value of the mean, the expected value of the mean, which is given by lambda. In lambda, we said it's given by the number of items, or what we were calling the sample size, times the probability of success. If this is not provided, that is how we are supposed to come up with our lambda. So lambda is a arrival time expected to be for the mean time where people will be coming in that behavior following Poisson distribution. Then for the exponential distribution, as we get into the cafeteria, there is a way into which will be a service, like what we were saying, the cashier at our banking Terra points may be serving us, let's say 30 customers per hour, or let's say one customer for every 20 minutes. So in such a scenario, we will take the mean on average, on average. Of course, will be serviced differently depending on our needs. Like there's a student who is paying with a cash, there's another one paying using a check. So those two modes of payments are going to be serviced differently. The time that somebody is going to wait until the check has been approved to a point that now the money can now be transferred into your account. Of course, the service time will differ from somebody who has the cash in 2-3 minutes she has been attended to. You see, our service time is going to be different. And the same with the pattern to which we are going to arrive. Say there's one customer coming in the morning, maybe in that particular facility, they come like 20 of them at a go, like the students during break time. The behavior of arriving, it's so different from any other time. During lunch hour, you are so many also. But come maybe at 8 to 9, no one is getting into the cafeteria. You see, but for us to be able to do the workings and of course to follow the theory, that's why we are taking the figures to be on average. So the service time is going to be exponentially distributed with a mean given by the mu, assuming that our behavior is emanating from the population. So that is and remember, we said that the value of the mu is actually given by 1 all over beta in reference to our exponential distribution. We also had the exponential distribution relating so well with time in our analysis in the probability theory. So those are two things that I want you to have in mind. Number one, the arrival time is Poisson distributed with a mean of lambda, and the service time is exponentially distributed with a mean of mu equivalent to 1 all over beta if that is not actually provided. Okay. Something else that we want to maybe look at is the way we are actually served at the different service points. Like in the cafeteria, in a hospital, you go, you queue for you to be attended to the doctor, to be attended to by the doctor, in a petrol station, in a cafeteria. So how are we normally served as customers waiting to get the service? How do we receive the service? There are different ways. Number one is what we call the first come, first served, which I believe is so common in so many areas where people would come in. If I find you that you are already in the queue, I join you, but after you, meaning I'll be serviced after you have been served in that particular facility. The first come, first serve, which I believe we all feel that there is the essence of equity in regards to how people are getting the service. Number two is what we call the last come, first serve. This one is not so common, but it happens, especially when, I don't know, when people knows others in the facility, may find that somebody who came in last is the one now receiving the service. It may happen like you come in and you pick a raffle ticket, and then you happen to be called first before somebody who had come in like in the morning, still waiting to get there, the service. Another one that is kind of common, especially where people are so many waiting to get the service, is that which happens at random. We just come into the queue and we pick just one person or a group of people. We say, all of you get in and you get the service. So you find that maybe we are picked in batches. Let's say the queue up to number 10, all get in, and then you find there are so many service points. So each one of you will get into different service points. And as such, you find there's somebody who will get the service before you, or there's one who came in first and now he or she is lucky to still get the service first before another person. Then in the hospitals, this is so common. You are waiting to be attended to by the doctor, and your case is not a severe one. So when an emergency arises, you find that there is a patient brought in, of course, you'll be told to wait. That is definitely going to happen, that you'll be put on a hold as we attend to that person who is urgently requiring the service. So in such a scenario, we talk about service and a priority. Also in the supermarkets, assuming you have a very small baby, the baby is crying a lot, you may find other customers giving you away, of course, to be serviced. In the supermarkets, they have also put in, like if you go to some of these big supermarkets, like the one at TLM, you find that they have a point at which they serve people who are disabled, people who are, for example, having issues with maybe small babies. As such, they'll be served under what we call priority. So those are the common behaviors upon how customers are actually served, of course, at different facilities, depending on like the style you use in the facility. Even in the bank, there's that point of providing services under priority, especially to people who could be having some challenges. The customer behavior. How do we behave as when we get into the facility? We have said our belief is that we will come in and join the queue. Then we wait maybe for a few minutes or for a few seconds, and we get into the service point, we get the service, and then we leave. But at some point, we exhibit what we call a level of impatience. And in this case, we show our behavior as customers who are not patient enough to wait until we get the service. So what are some of the characteristics that we can define for the customers who are waiting in the queue? Number one is what we call bulking. And this is where a customer comes in. It's so common again in places where we are trying to get let me use this example, the services provided by the government. Or even in the banking halls, at times like at the end of the month or at the beginning of the month, where most people are making payments through the banks, yeah? So you come in, you join in the queue, and you are eager to get to the service point, but now you find that you took a ticket in the bank, and then you hold on to the ticket, I don't know, for an hour, another 1 hour, you feel no, you just leave. That kind of a behavior is called bulking. You come in, you join the queue, but because the queue is too long, you find that you have got no time, you just leave the queue. Of course, you imagine of yourself staying there longer than the way you have stayed. So you find that maybe you have got no time anymore to see yourself in that particular queue, and you just come and leave. Lineaging is another kind of a behavior where you may also join in the queue, and you quickly think about your time, and you consider just to leave the queue. Priorities, as we had talked about earlier on, there are people who will be prioritized much more than others, of course, depending on the situation. So you may find that there are people who come in, and because they are in that category, they will get the service maybe immediately. Or maybe because you are a senior person in the government, maybe docket you hold in the senior government position, maybe you get the service somehow faster than other people. But you can imagine how is it feel by the other customers who are waiting in the queue. But of course, it also depends on the capability for people to be prioritized sometimes. Like I use an example here about the train. Assuming you're picking a ticket, there are those who use their money to book for a first class kind of a ticket, others the first class. So you find that those who are prioritized more are those who are going to pay higher than those, for example, who are in the second class category. So as a result of that, you may find maybe because the chances in the first class category is also maybe for a few, you find that when somebody comes in and she is capable of paying for the first class ticket, you find that that person is being attended before another. That kind of a behavior can also be shown to happen in the places where we actually queue. And the last one is what we call joking. And this is a behavior where it's so common in the supermarkets. You look at the cashier attending to someone, and then the customer who is being attended to, I don't know, she wants to pay using M-Pesa, the M-Pesa is hanging, and then you're still waiting there to be served. And then you find another cashier is now almost like done with the customer that this person is, or rather the customer she or he is attending to. So you quickly see that queue, and you find that it is shorter than the one that, for example, you are in, and you join in that other queue. But unfortunately, at times, when you try to move from one queue to another, you find that the problem to do with the network was not with the customer you left hanging when she or he wanted to pay through M-Pesa. It is like it's a network problem in the whole place. So you also find that this other queue now has hung in a manner that the customer whom you felt is likely to be leaving in the next 1 minute, he's now staying there for like, I don't know how many more minutes. So you now see another queue, yeah, which is getting shorter, and you move and join in this other queue. So that kind of a behavior where we lose patience, jumping from one queue to another, is the one we call the joking behavior. And of course, it's so common, at some point we feel that we don't want to waste a lot of time queuing. So that could reach to us moving from one queue, for example, to another. Or like bulking, we have said, you come in and you find that the queue is too long, you just leave, and you feel that your time is going to be wasted, so you don't have much of the time to waste, and therefore you just leave. Lineaging is a situation where, again, because of our impatience, you join the queue maybe a little bit, and then you find this queue is maybe getting longer, so you just find yourself leaving the system. Priorities, of course, depending on what is that you're getting as a service, may lead us to be prioritized more than other people in the same facility. And joking is a situation where you are moving from one queue to another, trying to get to be serviced within the shortest time possible. As we do our questions, as we had said earlier, the following is now important. How do we operate the queue system? It will have the following characteristics. Number one, the average number of the customers waiting for the service is called the queue length. That line, we call it the queue length, those who are waiting to be serviced. And then the average number of the customers in the system, that is those who are in the facility. The students who are in the cafeteria are who? Those who are eating, those who are already paying for their services, and even those who are getting into the queue or that particular line. All those are now going to be determined as the number of the customers in the system. That is those in the queue plus those who are getting the service. And number three, the average time a customer waits in the queue before he or she is serviced. That is called the waiting time in relation to the queue, the average waiting time in relation to the queue. And we also have the average time a customer will actually spend in the system. In the system means the time you spent in the queue and also the time to which you got that particular service until you are able to leave that particular facility. In our analysis, we shall consider only one model, that is a single channel system, where we will take the following, as we had mentioned earlier. Our service time is going to be exponentially distributed with a mean of mu, and the arrival time is going to be Poisson distributed with a mean of lambda, and lambda, we said if it's not given, you just get it as the number of the number of items involved. Of course, in the given area of study, there's a sample size times the probability of the success, assuming you are analyzing a question to do with probability. And then we will assume that our facility, the way we open our facility, that facility is going to be continuously opened. That is, we will not have a close point of the facility. And that's what we'll take as an assumption number two. Assumption number two there is infinite queue length. In other words, we believe that every other time the customers leaves the queue, others are coming in, and we leave it open. It's an open-ended kind of a system where it is going to go on indefinitely. And those are the guiding assumptions before we now look at how we got about the calculations. I shared this yesterday so that you familiarize yourself with the formulae. These formulae, remember, they are not going to be provided during exam time. So it's upon us. We do as many exercises as possible as a student so that you familiarize yourself with the language of the queuing theory, so that whenever a question comes in, you can be able to tell in which angle are you going, for example, to solve the problem. So this formulae will help us to, of course, understand what am I computing. Like if I want to know what is the service rate, I must come up with the service rate, I must come up with a mu, which we have said it's exponentially distributed. Then we also have the arrival time, which is Poisson distributed with a mean of a lambda. And without these two now, you can't be able to do anything in the queuing theory. So the very first thing, the moment you read through the problem, first of all, what is lambda? What is mu? Once you know those, you'll be able now to use any formula that you have here, of course, depending on what you're actually computing. So if, for example, you want to know whether the facility is busy, on point number 3, you cannot. This defines the facility being busy. here we mean that the facility is busy. In other words, it is not idle. The utilization factor means the facility is busy, that is, it is not idle. And we can also say if the facility is busy with this particular utilization factor, how about its idleness? Its idleness will now be given by 1 minus it's being busy. 1 minus the lambda all over mu give us the chance at which the facility will actually be idle. Idleness means you go into the facility and you find that there is no customer. So you found the mechanic, you found that particular cafeteria attendant waiting for you. He is even sitting there. That kind of a situation where he's not doing anything is what we call the idleness. So the facility being busy will be given by lambda all over mu. So it's being idle, you take 1 and you minus the chance of it being busy. The waiting time, because this was one of the things that we said it's important for us to evaluate. The waiting time in the system will be, you have the person waiting in the queue, and now he's still waiting for him to be serviced. And at the service point, how long that particular person is taking is also important for us to look at. And this will be computed as 1 all over mu minus lambda. The queue itself, how long are we going to wait in the queue? This will be given by the formula lambda. We divide this one by mu into mu minus lambda. Now, for each of the analysis here, let me talk about number 4. Number 4 goes with number 6, and number 5 goes with number 7. The waiting time in the system is given by 1 all over mu minus lambda. The average number of the customers in the system, including those who are in the queue and those who are in the service point, is given by, you take your waiting time, you multiply by lambda. So this is given by lambda all over mu minus lambda. How about the waiting time? Waiting time that is in the queue, those who are in the line waiting to be serviced. This is given by lambda divided by mu into mu minus lambda. To get to know the number of the customers waiting now, waiting in the queue, this is given by, you just take your waiting time for the people waiting to be serviced, that's the ones who are in the queue, and you multiply by again lambda. So we end up having, if you multiply this one by lambda, you will have lambda squared on the numerator, the denominator remains the same. So that is a hint that I can give when you're trying to use this formulae on how to work on anything that has been requested for in relation to the queuing theory. And because I was talking about the facility being idle, you just take 1 and you minus the chance of it being busy, to which it's given by 1 minus lambda all over the mu, giving you the chance of the facility being idle at any point. And other questions may come in the language of probability. For example, what is the chance of having no customer to be served? This will be given by P0 plus P1, where our P0 is equivalent to the chance of the idleness of the facility, and our P1 is the probability of having the number of customers in the queue and customer being served. The probability of having the zero number of customers in the queue, and you also have 1 customer who is actually being served. So you take that chance of the idleness plus now the whole of this, giving you the chance of having 1 customer being served and of course having no one waiting in the queue. Then you could also be interested in getting other probabilities. Like for example, what is the probability of having more than this is a common question, more than a given number, let's say 3 customers in the queue. How we get that? Of course, you get the chance of the facility being busy. You raise it to the power of, to that n number of customers quotient, you add 1. You add 1. The probability of the facility being busy, this is lambda all over mu, that is the chance of the facility being busy. You raise it to the power of n plus 1. But of course, as we sing about this, our interest is actually about whether we understand the problem or not. To use the formula, it's not a challenge. The point is, can we understand what we are being asked to compute? Because the confusing words comes in whenever you're asked about the system, whenever you're asked about the service, whenever you're asked about the queue, which one do you go for? That is the most important thing to distinguish before you come into the use of the formula. And once you know how to interpret the language now in regards to what is being asked in the queuing theory, I suppose when you now practice on how to use a formula, you'll be able to have the understanding and of course the remembrance, because this one I've said they'll not change, the remembrance of how the formulae are looking like. So to start with,